Hey, hope everybody's doing well today. Staying warm. I heard it's been pretty cold. Today we're going to go over the end of chapter or 11.1, section 11.1. I'll go over your homework problems because those are going to be very similar to like test problems and things like that. So I'll go over those, and then there's just a little bit of 11.1 left, and then I'm going to get you to do some of the section review because I think it'll be good for you to help distinguish like how work changes, how energy transfers, like how things like that work, and that's what those problems look like. So I'll have y'all do those, and that will be 10 points. And Coach Reese will give you credit for that on Thursday, tomorrow. And, on Friday, he'll give you credit for that. And, I haven't decided if I want to go into 11-2 for Friday, or if I'm going to just do a review and give you some problems to do for that. I will let Coach Reese know. That way you just won't have to sit here and listen to me lecture on something that it's going to be tough to remember a week later anyways, and you probably could care less about it, especially with spring break coming up. So I think I might just do some in-class work for you all. And that way you can get ready for spring break and not really have to worry about anything. And when we come back, we will just quickly review 11.1 and then move to 11.2. That way we don't waste a lot of time reviewing a bunch of material that you might not have remembered. Okay, so let's look at the practice problems. On 255, I think I said 6 and 7. So it says, a 90-kilogram rock climber first climbs 45 meters up to the top of a quarry, then descends 85 meters from the top to the bottom of the quarry. If the initial height is the reference level, find the potential energy of the system, the climber plus Earth, at the top and the bottom. Draw bar graphs for both situations. You don't have to draw the bar graphs, but we're going to find the potential energy at the top and the bottom. Okay, so first we know that the formula is UG equals MGH. Okay, that's the formula we're going to use. Okay, so we know our reference level was the initial height, I believe. Yeah, the initial height is the reference level, so that's always very important to know. Because that would change the way you do the problem, okay? So the initial height is the reference level. So first we're going to do the top, find the potential energy at the top, okay? So we have the mass is 90 kilograms. Our G is 9.8, and our height at the top, if we're going from the reference level, is 45 meters. Because it says that climbs 45 meters up to the top of a quarry. Okay, doing that, you get 4 times 10 to the 4th joules, okay? Okay. All right, and now that we found the top, we have to find the bottom. We are going to use the same formula. You're going to have a different height. All right. You've got UG now. Equals M times G times H. All right, still the same mass, so we'll we'll use the mass that you used in the first part, 90. Gravity is still the same. It's 9.8. Okay, now the only difference here is the height. Okay, so you have to read the first part of the problem again to see how you calculate the height. It says, he first climbs up 45 meters, okay? So, and then his final, so you have initial minus final, okay? So he climbs up 45 meters, and then he descends 85 meters from the top to the bottom. So you have to do 45 minus 85, okay? Okay, that gives you negative 40. All right, so you have 90 times 9.8 times 45 minus 85, or negative 40, and that's going to give you negative 4.0, or 4, times 10 to the 4th joules. Okay. So it says he climbed up 45 meters and then descended 85. That's why you do 45 minus 85, okay? All right. Good. Okay. Number 7. It says, a 50-kilogram shell is shot from a cannon at Earth's surface to a height of 425 meters. The system is the shell plus Earth, and the reference level is the Earth's surface. A says, what is the gravitational potential energy of the system when the shell is at its height? Okay, we know that the reference level is the Earth's surface, so we just have to know that the height is 425 because that's at the height, and we see that from the problem. Okay, so we still use the same formula, UG equals NGH. All right, we got our height, or our mass is 50 kilograms, gravity 9.8. All right, and then we have the system at its height is going to be 425. That's how high it goes, right? Okay, so just multiply those together. All right, and you'll get 2.08 times 10 to the 5th joules. Sorry for that screeching. That's our radiator. We live in a really old building and don't have central heat, so we use radiators. So they get really loud and annoying sometimes. So I'm sorry. This one's really simple. The second part gets a little bit confusing, but not really, if you think about it. Okay. All right, 7b says, what is the change in the potential energy when the shell falls to a height of 225 meters? Okay, so now we're looking for the change in U, change in U. So the change in U is actually just going to be final minus initial. So it's MGH final minus MGH initial. Okay. And you got to think, can't you pull out something similar there, and then put the rest in parentheses. You've got M and G are both common in both of the formulas. So pull out an M and a G, and then you keep the H final minus H initial. And that's going to give us our change in UG. Okay. So all I did was pull out the M and the G because it was common between both terms. And then you just have the height, the final height minus the initial height. Okay. All right, so now we just plug in. So we still have our mass is 50. We still have gravity is 9.8. The final height, if you look at the problem, it says it falls to a height of 225 meters. All right, so it's fallen now. That would be its final height, right? So we have 225 meters. Is our final height, 225 meters. And its initial height from where it fell was 425, right? Because it went up. It was shot up 425 meters. So that was initially it, and then it falls. Okay, so our initial is 425. So we know we're going to have it negative, which makes sense because it's the shell casing's falling, right? Or the shell's falling, right? Yes, okay. So subtract 225 minus 425, you get negative 200, and then you multiply that by 50 and 9.8, and that gives you negative 9.8 times 10 to the 4th joules. This one might seem confusing at first, but it's really simple once you just know the change in UG is this. And then you can change it to this by taking out the common terms, and then you just put in the numbers. I'll give you all a second to write that down and think it over real quick. Okay. All right, the last thing we're going to look at is elastic potential energy. There's no problems for that. It's just kind of just to go over it. So maybe on your test, it'll be like, give me an example of where elastic potential energy might be stored, because it gives us some common examples. So that could be a potential test question. All right, elastic potential energy. So look at the string on the bow and figure 11.7 at the bottom of the page right there. It shows that it's pulled and work is done on the bow, storing energy in it. So it's being pulled, and it hasn't released energy yet, but it's being stored there. There's the potential for it to transfer into kinetic energy, right? So pulling the bow has this potential energy, okay? If you choose the system to be the bow, the arrow, and the earth, then you increase the energy of the system. And when the bow and the string and the arrow are released, energy is then changed into kinetic energy because now it's moving, right? It's not potential anymore. The movement has happened, and now it's kinetic energy. Okay? The energy stored in the pulled string is called elastic potential energy. Elastic potential energy is often stored in like rubber balls or rubber bands, trampolines, things like that. Okay? Energy can also be stored in the bending of an object. So you can bend an object, and there can be energy there. When stiff metal or bamboo poles are used in pole vaulting, the poles did not bend easily. Little work was done on the poles, and consequently the poles did not store much potential energy. Since the flexible fiberglass pole was introduced, record heights have soared. Okay? It all has to do with energy. The pole vaulter runs with a flexible pole and then plants it into a socket in the ground, and when work is done to bend the pole, as the kinetic energy of the runner is converted to elastic potential energy. Then, as the pole straightens, the elastic potential energy is converted to gravitational potential energy. And kinetic energy as the vaulter is lifted as high as 6 meters above the ground. The increased capacity for the pole to store energy is reflected in additional height. Okay? So basically all this is saying is that elastic potential energy can be found in things that bend, or rubber bands, or bow and arrows, things like that. Okay? So just know that, and how those kind of can transfer. How energy transfers is a huge part of this section, which is why I'm going to get you now to do the section review. We'll do 1 through 3 all, or 1 through 3 like A, B, C, D, A, B, C, A, B. Okay, you don't have to do the critical thinking, but the reason I want you to do this is so you can see how work is stored, like how work takes place, and then how energy is stored, and then how it's released, and how it transfers energy forms. Okay, so that's what you're going to be doing with these problems. You do have quite a bit of time to do it, but I would go into the next chapter or the next section, but I don't think that it will be best for us with spring break coming up. So I'll figure out something for Friday. Yeah, but for now, work on like 11 or 1.1, 1.2, and 1.3. I'll do 1.1a just to kind of show you what I'm looking for. Okay. It says, in each of the following situations, the system consists of a ball and earth. Draw bar graphs that describe the work done and the changes in energy forms. Okay, you don't have to do the graphs, but I want you to tell me how work has been done or not done and what the change in energy is, okay? So 1.1a says you throw a ball horizontally. Okay, in throwing the ball, we do work on the ball, right? Because there's a force when we throw the ball, and there's a distance that the ball travels, right? So the equation for work is force times distance. So that's how it's done. So also the changes in energy forms, it basically gains kinetic energy, right? Because it wasn't moving and now it is moving. So that would be the answer to number 1. You do work on the ball and it gains kinetic energy because it's moving. So yeah, you'll go through with the rest. The horizontally thrown ball is caught in a mitt, or you throw a ball vertically and it comes to a rest at the top of its flight. Okay, so I want you to be thinking about how the energy can transfer from one form to another and how work is done in that situation, okay? That's really important for you to understand and know, so that's why you'll be doing that. And if you do get done early, again, work on other homework or something like that. I just don't want to overwhelm y'all before spring break and then just have to reteach everything. But I think this is not too much for you to have to remember. So, yeah. All right, well, y'all have a good rest of your day, and I will figure out something for Friday. I might just go ahead and start teaching the section. I'll have to sleep on it and think about it, but yeah, I will let y'all know tomorrow. Have a good one.